Hi, my name is IGriess and I'm a junior studying biomedical and electrical engineering at CSU. I'm going to be looking at a power management system for a general radio system using the concepts I learned in ECE 311, 331, and 341. Let's begin by looking at the overall system. The system is made up of two subsystems, a rectifier and an RC circuit. I'm going to start by looking at the rectifier, the inputs and outputs to that rectifier, and how the individual components, the diodes, work. Then I'm going to look at the RC circuit, the inputs and outputs when you input a rectangular pulse to the system. And finally, I'm going to put the two subsystems together and look at the inputs and outputs through the overall system. So let's begin by looking at the rectifier subsystem. The purpose of a rectifier is to convert an AC signal, which fluctuates between positive and negative, to a DC signal, which is always either positive or negative. Let's begin by looking at the input and output signals of the system. So first of all, we need to figure out if the system is linear and time invariant. Right off the bat, we can see that it is time invariant because the components do not depend on time. No matter when you run the system, you will always get the same output. Now, in order to tell if the system is linear, it needs to have homogeneity and additivity. For the system to be homogeneous, we need to be able to take the input voltage times a constant and get the output voltage times the same constant. I ran some simulations in Cadence to prove that this is not homogeneous. In the graph on the left, the input is a 8-volt peak-to-peak sinusoidal. The input does not look like a sinusoid because the ground is on the negative side of V out. In the graph on the right, you have the same input sinusoid times a -1. As you can see, the outputs are exactly the same. So this is not homogeneous and not linear. You may have noticed from the graph that even though the input voltage is plus or minus 8 volts, the output voltage is quite a bit smaller than 8 volts, and that there is a small period of time between each output wave. Both of these things are due to a voltage threshold called VD on, that is required to turn on the diodes. This voltage is typically around 0.7, 0.8 volts, and you can solve for this voltage using electromagnetics. So to solve for this voltage using electromagnetics, we need to look at the model for a diode. A diode is a PN junction, which is made up of two semiconductors, the N-type being filled with an excess of electrons, and the P-type being filled with an excess of holes. When you put these two semiconductors together, a region forms in between them, where the two transfer between each other, called a depletion region. The voltage across this depletion region is what determines VD on. We can solve for this voltage threshold using the three graphs I have provided. The first of these graphs shows the charge density as a function of the distance across the diode. By integrating for the charge density, we can solve for the electric field. Once we have the electric field, we can integrate that to get our voltage. And our voltage graph gives us our change in V, which is equal to VD on. Now let's look at the RC subsystem. The purpose of this system is to store charge. Let's begin by looking at whether or not the system is linear and time invariant. Once again, this system is obviously time invariant because none of the components depend on time. You will always get the same output no matter when you run the system. And it also has to be linear because the voltage through each component depends on the sizes of the resistor. The equation for Vout in this case is R1 divided by R1 plus R0 times Vin. So if Vin is doubled, the output will also be doubled. And if you added two signals and use that as your Vin, your output would be equal to the sum of the two outputs of both of those signals. So this circuit has both homogeneity and additivity and therefore is linear. When you input a rectangular pulse wave into the system, you'll get a Vout like this. In the system I chose R1 and R0 as 1 kilovolt, 1 kilo ohm, so you get half of the voltage traveling through the capacitor and half traveling through R0. The exponential curve in the output is because the capacitor slowly charges and discharges over time. Now let's put the two subsystems together into the overall circuit. I ran a simulation and cadence of this circuit using a Vn value of 5 volts peak to peak and plotted V rectifier and Vout. As Vrec rises, the capacitor in the RC circuit begins to charge. Vrec reaches its peak and then it starts to go down again until it is equal with the Vout. At that point, there will be a large enough current from Vout to turn off the diodes. Then at this point, Vrec will follow Vout until Vn is large enough to turn on the diodes again. Because with the diodes off, no current can flow through R1. The cycle continues and it will eventually become periodic when the amount the capacitor is charged equals the amount it is discharged. If we were to use alternating current in our computers or TVs and other electronics, they would constantly be turning on and off. So this is why this component is so necessary. This component allows us to convert that AC signal into a DC signal. By tweaking the resistance and capacitance values, we can also keep that DC signal within a certain range so we do not fry systems with too high of a voltage. The power management system is a vital component in our electronics.